Hello folks, my name is Chris Sensor, and today we're going to talk about Tract Signed Well in Siemens Simcenter Test Lab, versions 2021 and earlier. And we're going to talk about why run a Tract Signed Well test at all. We're going to talk about how a phased Tract Signed Well test works, the basics of running a signed well test, and then we're going to do a live demo. So, why run a Tract signed well test? Well, signed well testing in general simulates a worst-case vibration environment. We've all seen videos like this with a wine glass excited by some type of acoustic frequency at resonance until the wine glass shatters. What phased Tract signed well does is ensures that signed well test will stay at resonance for the duration of the test. What do we mean by that? Well, your resonant frequency can change as a part changes temperature or fatigues, or if a part is nonlinear, as we increase the level of excitation, the frequency of resonance can shift. So if we remember our basic physics equation, omega sub n, the natural frequency, is equivalent to the square root of k over m, k being stiffness and m being mass. The stiffness, as a part changes temperature or fatigues, decreases. So the natural frequency will decrease as well. Now, in a complex nonlinear structure, we also have this phenomenon where different levels of base excitation are also going to change the response frequency. But even though the resonant frequency can change, the phase angle at resonance stays the same. So we can use Tract signed well to keep on that phase and make sure that we're testing at resonance the whole time. And then what you can do is build in a formal high cycle fatigue type of test. You can build your SN curve, also known as a Wohler curve, or you can more informally gauge the life cycle of a DUT by running at resonance for a specific number of cycles or time period. And then you can say with confidence that your product is going to meet or exceed its warranty period, for example. So the way phase Tract signed well works is we look at the phase at resonance, and we can see here three examples of what happens when you're below, at, or above your resonance frequency. We can see that in a perfect single degree of freedom system, when we are below our resonance frequency, we have a 0 degree phase shift, and the motion of the response mimics the motion of the base excitation. At resonance, we have a lag of 90 degrees, and our response motion is higher than our base excitation. And when we get above resonance, our phase shift is 180 degrees, and our response typically is less than the level of the base excitation. So the way signed well works is we're looking at that phase angle, right? And as a part fatigues, we're looking at whether that phase angle is changing, and then we change the excitation frequency to match the resonance frequency. More information about natural frequency and resonance is on our community website. Address is down here, and this is a full discussion of natural frequency and resonance, all those things. So what we're going to do here is first we run a low-level sine sweep to identify the resonances. We use the information from that sine sweep. We calculate a frequency response function and determine what the phase angle is at resonance. Then we build a dwell table, because a complex structure or part could have multiple resonances across our frequency range of interest. Then we decide how long we're going to dwell at each resonance. And as an option, we might decide to control the amplitude of our dwell from our measurement point as opposed to our base excitation point. We'll explain more about that later. And then we run a dwell test. So this is our setup here. We've got a shaker, we've got a little cantilever beam structure, and there's a control accelerometer that we're using. That's going to be our base excitation. Then we have this measurement accelerometer at the tip of our cantilever, and we're running a SCADIS with a VB80 card. And this is what I was talking about before. You can choose when you do your dwell to run at an amplitude based on your control accelerometer, or you can run at an amplitude based on your measurement accelerometer. So this typical kind of situation is that we have some kind of strain gauge we've investigated previous to running this test, how much strain we need for building our Wohler curve, and we figure out how much displacement gets us the requisite amount of strain. And so when we run our test, we know that we need a millimeter of displacement, for example, to get our point on the Wohler curve. Now, you might ask yourself, why not just control off of strain? Well, the problem controlling off of strain is, of course, strain gauges don't tend to survive the entire length of a sine dwell test. They either pop off, the solder points loosen and fall off, or the strain gauge itself just falls apart. Those thin foil type strain gauges. So that's why we use either an accelerometer or more typically a point laser at the tip of our cantilever beam to measure what our displacement is. So here we are in the Simcenter Test Lab Tract Sine Dwell software. We have set up our channel table already with our accelerometer values, and in particular take note of channel 1 and channel 2, which are going to be our reference control and our response control in the Z direction, which is normal to the cantilever beam surface. Next, we go to our sine setup, and we're going to input some low-level sine sweep. In this case, I've chosen 0.5 G sweep level, and we're going to sweep from 50 to 500 hertz. I know from experience that this beam is going to have a couple resonances below 500 hertz, and you might take that information from an FEM model or some type of modeling that you've done before. If you don't know where your resonance frequencies might be, you might take this information from operating conditions. For instance, you know the typical operational RPM of your jet engine in flight, so you're going to do a sweep from maybe 5 hertz or 10 hertz, whatever that low frequency of your shaker is, up to the operational speed of your jet engine. So over here, we make sure that our min and max frequencies line up with our sweep. And we also want to make sure that we turn on our frequency response function measurement. This is going to give us a very accurate phase angle for our dwell. Next, we'll run a self-check. The self-check is going to take a look at all of our accelerometer channels and make sure that everything's working right, that the ICP power is responding correctly, we're measuring the right voltage, and then we're going to start doing some excitation. Now we've started to do some basic excitation. We're measuring transfer function between our drive and our response, and we're looking at things like coherence and signal to noise ratio, and again, just making sure that everything makes sense. Self-check is very, very important when running a test, and you can pretty much tell from the self-check data whether a test is going to give you problems or not. So there you have it, our self-check data, and we can check on things like our DC noise, RMS noise, any type of offset that we might have, and this is very low, which is good. And we see that our signal to noise ratio is extremely good here. And of course, we look at things like the coherence, and you might think at first glance that this is maybe not great coherence, but you have to think about scaling. Coherence is a value between 0 and 1. So if we fix those quantities, we can see, in fact, that we have great coherence on these response and reference channels. We'll change that here again. And again, you can see our coherence is almost 1, which is a great scenario to have when you're doing this kind of sine testing. So now we're going to go and run our sine sweep. I'll hit ARM. Now the test is ready to run. We'll hit start. You might hear in the background our sweep starting, and you can see this fuchsia trace is our resonance response, and the blue trace is our control accelerometer. See some nice resonances develop here as we go through the sweep. If we look at these bottom traces, we can start to see the change in phase as we go through some of these resonances. Don't be fooled by these fast changing phase angles down here. All this is a phase wrap situation. Minus 181 is the same as plus 179. So as that phase changes, sometimes it looks like we're oscillating back and forth. It's a phenomenon called phase wrapping. And so we've completed our sweep here. We can see 4 nice resonance peaks. And now we're going to go into our dwell setup. And we're having our FRF displayed here. And we've identified 4 resonances, but let's pick maybe the top 2 here. So we'll go with this about 80 hertz resonance here, and we'll add this to our dwell table. And we'll also pick this about 280 hertz resonance. We'll add this to our dwell table as well. Now, down here, we're going to change from a fixed dwell to a phase tract dwell. We're going to increase our reference amplitude. This is based on the sine sweep we defined, but we don't want to dwell that amplitude. We want to dwell maybe at a much higher amplitude. Now, you might say to yourself, well, 50 G seems like an awful lot. It is. So this we're going to do as an example to show how we can do our dwell based on a displacement at the tip. So we'll do for 60 seconds at each frequency. Now, if you want, you can also define this in cycles by changing this drop down here. But for now, I'm just going to stick with a minute each. The other thing you frequently have to change here is this lower frequency. This is a pretty tight lower frequency bound, especially when we start to track at our initial amplitude here. So we'll see right away when we do this dwell that we're going to start at this frequency and immediately start to shift down because we have nonlinear structure. So I'm going to change these lower frequency bounds to give us some room to shift. Now, typically you don't see an increase in frequency unless your test article is going through temperature cycling and gets cold. If our test article gets cold during the test, you'll see an increase in stiffness, and remembering our omega equals square root of k over m, as something gets colder, it gets more stiff, and then that frequency will shift up. That's a very rare case in testing. The last thing you almost certainly want to have is these over time measurements, and this is going to track the amplitude over the duration of the test. And we'll see when we go to run the test why this is so important, but just kind of a basic understanding here. If you just look at the frequency domain data, you're going to see a point, and maybe that point will shift over time, but just looking at the frequency data is not really an indication of what's happened over the entire length of your test. So these over time channels are going to plot the amplitude at each second or so of the test. And so we'll see that. The other thing to change here, maybe if I'm tracking on a displacement, I might want to change this from an acceleration curve to a displacement curve in my Tract data. One more thing you might want to do is change the between dwells mode from sweep to step. The last thing here, and this is optional, is going back into the Sine setup and setting a notch profile. This is going to allow us to use displacement to determine the amplitude of excitation. So what we're going to have is at that 80 hertz frequency, we're going to dwell at a 0.5 millimeter, and at that 280-ish frequency, we're going to track at 0.05 millimeters. So now that we've done that, we're going to run another self-check. And now our self-check is complete. We'll go right to dwell control and arm the system. And now we can hit start and start running our dwell. And we can see, as I mentioned before, that our frequency shifts down immediately till it hits a stable frequency of excitation. And we went from that starting frequency of about 80 hertz, now we're down to about 77.25 hertz. And we can also see that even though I set my excitation level to 50 Gs, my base excitation is only about 1 1/8 Gs to get the displacement result that I want at 0.5 millimeter. Now we've reached the end of our first dwell, and we're going to move to that higher frequency dwell. And we can see again how we went down in frequency to about 272 hertz, down from starting at 285. And again, even though we set our dwell to 50 Gs, our base excitation is only about 3 Gs here to get the displacement that we want. The other thing to note here is we have very good control of any overshoot this way. That can be a real problem in a sine dwell test. If you have any overshoot at all, sometimes that will invalidate the test. So that is the end of my Tract sine dwell demo, And thank you for watching. My name is Chris Sensor. You can reach me directly at chris.sensor@siemens.com or respond in the comments on our community site in our Phase Tract Signed Well article.